It's so blue, it's killing me. I mean, it's sorry. It is fucking blue. Okay, all right. So, oh yeah, Vincent, you will be asking me questions. So we have something called Riemann Sum, and we have been going very slowly as usual. Hopefully, Sophia will show up. No, no, that was Fermat with his equation that he wrote that he said I have the proof of it, but he probably was lying. Okay, so what is a Riemann sum? Anybody? What should I put here? Anybody remember anything? I, of course, am cheating. I've got the cheat sheet right here. So Riemann sum, if you can put R. This R here is not the R of the real numbers. This R stands for Mr. Riemann himself. You put the function here, and then what do you put here? Yes, please, you can come in. Folks, yes, anybody? No? Very good. Let's move on. What is this P thing? Does anybody remember? P is a partition that you divide, because what this little thing here actually has, and if I put a dot here, we're saying we have a tag partition. Partition of what? This function is defined over what? So inside this little thing here are a couple of things. This partition is a partition, as in tagged. So we don't have to worry about the length because we're looking at it abstractly. This is a tag partition of this thing here, a closed interval AB on the x-axis. So we have tag partition. And so in fact, what this whole thing is saying is that this function is defined on AB, and the area under the curve. This is the area under F. We will calculate by sticking what under the curve? STEM people. Those rectangles that I was calling triangles last time. Okay. Okay, so what's the how many triangles? Rectangles. Why do I go to triangles? Rectangles. How many rectangles would a Riemann sum have? Finite number. Let's call it n. Let's start at I equals 1. So if this is our graph, this is our F. Our AB is going to be here. Because we have a partition on the AB, this thing has been partitioned into subintervals. And so the rectangles, so let's say, I think I'm going to do this here. So this guy here will be our tag here, T1. So this is x1. This equals x0, x2, x3, and then this is x0, xn. So what's the height here, folks? It's the height of this thing. What is this thing here? Very good. And do we put x1 or do we choose randomly within this subinterval the best point so that we get the tallest or the length, height of the rectangle? So our base is this thing and our height is this thing. So since it's tag partition, not just simply partition, we don't have to worry about, if you've done calculus, you remember you do the left endpoint height or the right endpoint height, that would be x1, or this, or any point in between is what the tag represents. So we put here P of I. So that means I is going to go 1, 2, 3, 4, all the way to n. and then height times, so this is a rectangle, n rectangles total, times what? The base. And the base is x1, right endpoint, the bigger one, minus the smaller one. So if the bigger one is x of I, then the previous one, previous endpoint or the left endpoint would be I minus 1. So this is Riemann sum. All right, and we've gone through all of this before, and now we have to move on to what happens when we take the limit of this thing. And that's where we were last time. So maybe I'll leave this here. So this definition has an intuitive part and a formal part. And we need to kind of relate the intuitive part with the formal part to understand what's going on. So last time I said, so this was from this textbook by the author's name. The definition is 7.5. And before we actually look at it, let's say, we say I'm skipping some items here. We say, the author of this textbook says, we say that the Riemann sum, Riemann sums of F. You see that S there? That's interesting. Tend to a limit L okay as so the Riemann sums tend to a limit L as M of P. Oh, I forgot to do this M of P before. Mesh of P tends to 0. Okay, so what is mesh of P? Mesh of P is the widest, largest width of the base of these rectangles. If the largest one goes to 0, the rest of the ones will also shrink. So Riemann sums. So let's see, what does it mean for Riemann sums of the function f tend to a limit L? So Riemann sum was, okay, let's do this one here. This is, let's put 1 here too. A and B. What is this thing here? These rectangles represent what? If we, the area, if we add up these rectangles, we will get, so there are, so below this, I would say we have a Riemann sum, F of, and they might be tagged. We could ignore that right now. So we might have, how many of these things are we going to have here? One more. This is R, F, comma. So the Riemann sum here is, you can calculate the Riemann sum, which is the area, the approximate area of the region under this curve here, this curve F. Do we need one more? Right, each one of these represents a rectangle. All right, now what happens? So here we go. So this is 0 and this is 1 or something like that. We say that the Riemann sums, which one has the largest uh, uh, so mesh, this thing is M mesh equals uh, let's see, 2 minus. What is this thing here? These are the width, the lengths of each of the bases of these rectangles. So, and we put those into a, this is another way of thinking about a partition. So a partition, once you partition the closed interval AB, you get these subintervals, but each subinterval represents also the base, the width of the base. So we took each of these subintervals that we've seen in the previous 3 classes, and we put them into a set, and then what's missing here? Applied the max function onto this set, and this will return the widest. This will be the max width here. All right, so this one here, let's suppose it's this one, this guy right here. Which one is that in our by inspection? If this is the widest rectangle with the widest base, which one is that over there? This one, right? Just by inspection, because we only have 3. And I only put like 2 here, so the third one is missing, and we go all the way. Now, thank you. All right, so let's go back. What is, we say that the Riemann sums, this is a sum. How many Riemann sums are there? Right now, no, this is one sum. Is that true? Yes. This is one sum. Let me give you another sum. And this is our second Riemann sum. Which one gives the better approximation of the area? This one or this one? How did I get from here to here? By making the largest width of the base smaller and smaller. As the width of these rectangles tend to 0, the area under the curve tends to a limit. The exact, this thing here is the exact area. And this is intuitive way of talking about this, right? So as we make the Riemann sums more and more, a better and better approximations of the area under the region of the curve, in the end, when you send this guy to 0, you will end up with, so this, the widest one, when that goes to 0, what you end up having is so many rectangles in the curve. So the error goes away. This is the error, right? The stuff in the red is not included in the area of the region under the curve here. Okay, so there is a more mathematical, so everybody understands this. This thing is basically the widest length. If you make the widest, if you shrink the widest length of the base, if you shrink the base of the rectangle with the widest base, that means what you're doing is you're also simultaneously shrinking everything else, because you're increasing the number of rectangles that you can fit in here. Okay, so how do we say this in the formal exact way? Well, let's do that now. And I'm going to go over this again probably very soon. If so, this whole thing is the same as this thing right now that I'm going to write. If for any epsilon greater than 0, there exists, or I can find a delta. There is a delta which is also a positive number. So if I have an epsilon, if I'm given an epsilon, then I can find a delta that is also positive, such that, okay, so I'm going to write something down here and then delete it and then go back to the textbook. So you are given a delta. This delta relates what? The Riemann sum with the exact area under the curve. So what is Riemann sum? This is Riemann sum, right? So for any given epsilon, so this thing determines the relationship between the approximate areas of a region under the curve minus the exact area under the curve. Okay, so if error is 23, okay, so let's say we have a curve and the area under the curve exactly turned out to be 100. And then the approximation that we got was, let's say, this is what we actually got. So then the error is, what's the error? It is less than, or it's actually 1. So let's do 9.5. It's less than this, right? So so if I choose, no, I chose epsilon to be 1, and these numbers worked. If I stick a bunch of rectangles, because I know how to calculate the area of the rectangles, God gave me the exact limit. Okay? Because God says that this function is integrable. This f, you can integrate it and find out the area. And then God said, hey, the exact limit is L. But what you have, what you're working with is just rectangles. Now you decide how exact, how much of a, how good approximation your Riemann sum will be versus what I tell you the exact area is. If I chose this to be 27 and 100 is the area, the exact area under the curve, then this would be, this better be what? What is 27? So that's 75, 73, 72. Will 72 work? No. Do I know math? No. Wait a second. Let's do this. That is easier. So this means this can't be more than 75. All right. 75 will work. It needs to be less than. Is this true? I'm just wondering. I forgot my math. This is not true, right? 76 will make it true? Yes. It needs to be less than 25, right? We need 76 rectangles under the curve because we chose a very large epsilon. So in other words, we have the curve here, and we need 75 of these. which means the delta has to be, and then which means how do I fit 75? Yes, it gets rid of the error. How do I make sure I can stick 75 rectangles under the curve? By making sure the width is of the right length. If I can get the right width for the largest rectangle that fits under the widest rectangle that fits under the curve, I make that width less than delta. So this is where the delta comes in. And so I needed to stick 76 rectangles. And in order to fit 76 rectangles, the constraint on fitting 76 rectangles is the width. If the width is too large, I'll only be able to put in how many? Maybe 3 or 2 for 76. And so we write here, let's see, M of P, the length of the widest, the rectangle with the widest base, the length of the base, which is the widest of the rectangle, should be less than delta. So let's suppose to stick in 76, our delta had to be 10. If each one of these is 10 centimeters across, 76 will stick here. What if I change the given to 1? If our epsilon is 1, if our error is 1, which means this has to be 99.5. We're back to that. Does the delta, does the delta, do I increase the size of the delta or make it smaller? Yes, thank you. There you go. So, and that is a relationship that's going on here. All right, so now I'm going to, you guys kind of understood what I'm going about this business. It's the same kind of relationship as, so now I'm going to, I think I can leave this here. Let's see. All right, so such that, rewrite this thing here. So what do we actually have? We have the Riemann sum. Then we also have the actual limit, because we have assumed the function actually has a limit, and that limit of the Riemann sums is the actual integral, the actual exact area. We're given the epsilon, and we are given the Riemann sum, and then we are asked, is this if you have this Riemann sum and God is telling me this is the limit, is this true or not? It's going to be true if we can find the right delta for it. Okay, so this condition that I wrote and the other condition has to be true. That means the limit exists. Okay, so we have such that if P is any partition of AB, so I need to, oh, this is the wrong, trying to, it's a very weird looking jacket, by the way, the one I'm wearing, so I'm taking it off. It does hide my neck. This one, I've been looking at Dr. House's neck constantly on that show. Actually, his throat. No, that show is fucked up. Okay. If P is a partition of this AB with So if we have a situation where we have partitioned the closed interval on which the function is defined, and we've got the right widest length of the base for our rectangles because it is uh, smaller than this delta that we made, uh, that we figured out from the epsilon that was given to us. Because this statement happens first. Given this, find this. This is the basic definition of then. So what do I write here, folks? This was one of the things, and the other one was, if we know the correct, if we have the correct width of the basis, the correct biggest width for the all the of the widest, sorry, one of the rectangles which has the widest base, which means this one is going to be very small. Then, and then what's the other is condition that needs to exist. So we can say that the Riemann sums are tending towards a limit. Once the difference between the Riemann sums and the exact limit that God gave us is less than. Ryan, are you remembering this? Yes. Okay, very good. The error epsilon. All right. So we're going to write here what? Riemann sum minus the limit is less than epsilon. So this is the formal way. Do you guys remember the definition of a limit was exactly like this, a limit of a function. So we are actually using the limit business here. Do you see limits here anywhere? This is informal. So what's happened is what got translated was this thing here. If you take the limit as, let's see, as I goes to infinity of a Riemann sum. This is the third way to this. If we take the limit to infinity of all the Riemann sums, this will be equal to this thing here. All right, folks, if this is true, if this is the situation, then if this and this and all of this whole thing is true, then we can say that this L here is actually equal to so when you see this formula, what is this? Definite integral or integral, I can't say that. From A to B of fx times dx. This, if you write it like this, this is this thing is this guy. If these conditions are true, then L actually, we usually say L equals this thing, which is what we, because if you take the limit of this thing, what's the other way to write this? You've got 1 and this giant box here. Let me make it into the red. This box and this box. This box resembles this, doesn't it? Without this part here, right? But this box and this way of talking about a definite exact area under the curve, exact area of the region under the curve is exactly, these two things are same, and we can either write this out or write this out, or we can write what? Yes, very good. The snake. All right. So now, I don't know. Did you guys have to look at the PowerPoints, I think, before how much do you got how much do you get, Gavin? 70, 80, all of it? 60. Okay, where is your confusion? Point. Tell me where you are confused. This thing? Oh shit. Okay. Huh. Should I okay. Okay, here's something. Maybe this will help. And this is memory. If I write limit of this function f as x goes to, what should I write here? Let's say x goes to infinity equals L. So the limit, what a functional value will fx get when x goes to infinity? It's going to get this number. So what is another way to say this? And this is when I'm trying to remember this. Shit. We're going to have and then this bit here would have been, sorry, C here less than delta. As the values in the domain go towards C, then all the fx's, the functional values go towards L, actually, and I can draw that up here. Okay, Sophia, we needed you because you could have slowed this down and then Gavin would have got the whole thing. Fucked up. Okay, so where was I? So here we go. Here is a situation. This is a point C, and as x's go towards C, the function tends to its limit. So as x's, so this could be, let's say, 5. The f of x's tend to, so the limit of the function right now is what? As we put values closer and closer to C, all the x values closer and closer to C for this function f, the functional values tend from both left and right towards this point, which is not even defined and doesn't matter. So the limit exists and it is 5. The value of the function doesn't exist, and therefore it's not continuous because there's a hole there, but the limit exists for this function. What we're doing with that is similar. The approximate area versus so the limit versus the actual function value. So it's a similar kind of situation. You have the approximate area and then the actual area. And their difference better be less than epsilon, as in when the difference between the functional values that are closer and closer to the actual limit value, the difference between this and this better be within epsilon. And how did we show that? If you guys remember, this would be L minus epsilon, and then this would be L plus epsilon. So in this case, our pictures are not, they don't look like that. Our pictures look like this. So this is where the rectangles are getting closer and closer to the big general area. So if you look at my PowerPoint, I've tried to make pictures where, so this tends to, as long as, and now what do we have here? We have crammed this region under the graph with so many rectangles that it's working out. So this thing here is this guy, and this bit here is the width of the, when the width of the largest rectangle in the curve goes towards 0 or is less than a very small positive number known as delta, then what you actually have is not rectangles, but what you're actually getting is the exact area under the curve, not an approximation. Okay, so that is why the same definition works for functions, and it's very similar to that. Everything is defined usually like this when you have a couple of things. So in this case, what you're given, just like with this, what's given is this. You use the error difference between the functional values that are very close to the actual limit. You figure the delta from this guy. Once you figure that, then you do a direct proof. Which did we ever do that? No, we never did that shit. Should have done that. Okay, all right. Where are we? We have like 8 minutes. I'm just gonna write down the proof, or write down another definition. And is there something else here? No? Okay. We've spent a lot of time. So this is it, folks. No, well, this could be it. Do not do that again. Yeah, do. Oh, shit. Okay. Remember, you're going to get a ticket like I got. Okay, Ryan, you understand everything, right? Solid. Have you seen this definition before? You taken real analysis or no? No? Okay. All right. So this bit here is actually a lie. The definition itself is exact. Okay. So there is a proof. So let's start looking at a theorem today. You missed something, but yeah, maybe I'll do this again on Wednesday and you can ask me questions if you're. Yes, because nobody was asking me questions. She was too busy drinking the milk or honey. Malak Sahab, what are you eating? Olive. Oh, with chopsticks? Are you like a bad Palestinian eating olives? Hmm. Yeah, I'm worried about my reproductive rights, so I'm voting for Kamala Harris. America, put your women first. America, I love you, America. Okay, we're gonna talk about America from now on. Let's see, theorem. Have I misspelled this? No. Jake, how much did you get? 60, 70%? Whoa, I like that number. So your error was around 17%. Yes. So Jake's understanding, which is, what was that, 83? Minus, if Jake had understood 100%, and your epsilon, your error was reasonable for you, 17%. If we increase the error and your understanding, so now we want the epsilon to be 40, then your understanding goes down to 60. That's what's going on. Yeah, yeah. Oh, all right. So if, all right. Okay. We have 6, 7 minutes left, so we'll do just one cool thing. What does this say? Very good. F belongs or is, F is if one of the functions that belongs to this set of functions. So this is a notation. And what is this set of functions? All the F's in this set, in other words, this thing is equal to a bunch of different functions like x squared, x cubed, whatever. So these functions, these bunch of functions, we can figure out the exact areas under this function. In other words, all of the functions that belong to this set, this is a set, are integrable. In other words, all of these functions that are hovering over our closed interval AB, you can have this one, maybe it goes like that. All these functions we can calculate are integrable, Riemann integrable. That's what this definition says. In other words, if we have a situation where what is true? And so what we have an instance of a function whose exact area can be calculated because it's one of those functions that are Riemann integrable. Okay. Then, if this is the case, then the theorem says then the value of the integral is unique, or as the book says, uniquely determined. So this is the theorem that we have to, so this is all we get in the theorem. So how do we translate into the math? If this function is integrable, that means the Riemann sums of this function that we calculate will have a limit, which will be this thing here. This thing, another thing for this would be the L. Integral is the limit of Riemann sums. Yes? Okay. So yes, so what this is saying is that we have a situation where we can fit enough rectangles to find an approximate area under the curve. Plus, if we send the width to 0, we can find the exact area under the curve. And that exact area is called the integral of the function, right? So this is another word for exact area. Okay, so we have a situation like this. If this is true, so let's expand this. I'm going to expand this, and what do we need for this? We have the integral. L belongs to R. It's a real number. Areas are numbers. That's all. What else do we need here? We need a delta and an epsilon. Okay, so we will have an epsilon, which is a positive number. This will be given. We also have figured out the right delta for the width of the rectangle. And we have figured out a partition for our closed interval for this F. That is, so we have a partition, tag partition here of the closed part, interval beneath the curve. And then we need, now we need to bring this guy and this guy. This doesn't look like a delta, does it? This is better. So I'm going to write this down. What's another way to say that? This is the mesh or norm. When you have two vertical lines together, it's the absolute sign thingy. This is actually absolute value sign, but this is for points. So it, whatever you stick it in here. So this is the partition, and we were using this notation before. If this was less than delta, this would be less than delta. So from this box here, we get all this information. Okay. And then the other thing we need to put a stick in here is this better be this better be true, which is, what is this saying? The widest length, the widest, the rectangle. This is the length, the widest length of the base of the rectangle with the widest base is what this represents, is less than this very small number. And then here we stick what we do. I'm going to still use R, and then F comma should be less than this guy here. Limit is less than epsilon. We're going to use this business to show that if a limit exists of a Riemann sum, it is only one number. In other words, this graph here, if I had, I'll draw it right here. This is L, and this is A and B. How many exact, if I say the area under this graph is 79, and then I say that area, and that is the exact number of this is the area. And then I say, and you know, sometimes the area under the graph is 83. Is that possible? Shit, why are you guys just hanging out? This is not a cafe. I've just voted for the bad Palestinians. That's a really bad joke. Okay, a best commie is a dead commie. That's my slogan.
My uncle works for ULA, so naturally he hates China with
Oh, with a passion.
never seen somebody care about something he hates.
Thank you.
Genuinely can't deal with it.
The fact
He
is,
hates communism.